Welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research, from advanced biomedical technologies to breakthroughs in AI, materials science, chemistry, and physics, all told as compelling, easy-to-follow stories. And, right now as you listen to this, there are just trillions of ghost particles passing freely through your thumb every single second.
Yeah, trillions. And you obviously don't feel a thing.
Right, nothing at all. But to catch even a handful of them, scientists actually had to bury a 10-story glowing sphere beneath a mountain in China.
It is honestly a phenomenal feat of engineering. And I think it perfectly parallels a broader theme we're seeing across completely different disciplines right now.
Yeah.
Like this whole idea of building highly intentional systems to detect things we normally just cannot see.
Oh, that is the perfect way to frame it. Because before we dive into the subterranean physics, I want to quickly look at a paper from the June 2026 issue of Nature by Guy and colleagues. They looked at child online safety.
Ah, right. The digital harm study.
Exactly. And the core finding is that online and offline experiences are deeply intertwined. I mean, a harm might originate in a digital space and physically manifest offline, or vice versa.
Right, which means our current protection systems are, well, they're largely reactive. They were built for an older offline paradigm where you basically wait for an incident to occur and then you respond to it.
Yeah, relying on downstream reporting, like waiting for a user to hit a report button after the fact, just doesn't work for the modern internet.
No, it really doesn't.
So the takeaway from the research is that society needs what they call safety by design integrated directly into the architecture of digital platforms. And they note these prevention strategies have to be impartially grounded in local real-world contexts to actually function. And, just impartially reporting your findings here, it is really a wake-up call that we can't just passively observe chaotic environments.
Yeah, you have to actively engineer safety by design to catch those invisible threats. The parallels to the physical sciences are just striking there.
Okay, let's unpack this, because you can't just casually look for invisible particles either, right?
No, not at all. You have to engineer extreme precision environments to trap them. Which brings us to the ultimate ghost particle.
So here's a strange question. How do you weigh a ghost?
Well, if we're talking about neutrinos, for a long time, physicists didn't think we had to. The standard model of particle physics originally predicted that neutrinos, which are the most abundant matter particles in the universe, by the way, were completely massless.
But scientists realized there was a huge problem with that assumption.
A massive problem, yeah. Because neutrinos come in three flavors. There's the electron neutrino, the muon neutrino, and the tau neutrino. And as they travel through space, they just spontaneously change from one flavor to another.
Which is known as neutrino oscillation.
Exactly.
But wait, hold on. I have to push back on the physics here for a second.
Yes, it.
If a particle is truly massless, it travels at the speed of light, right? And if it travels at the speed of light, it doesn't experience time. If it doesn't experience time, it can't change. I mean, it's like throwing a chocolate chip cookie across the room, but halfway through its flight, it turns into an oatmeal raisin cookie.
That would be a huge disappointment.
Right. And then when you catch it, it's a snickerdoodle. The only way that cookie changes is if it experiences time, which means it must have mass.
That is honestly a perfect analogy. You nailed it.
Yeah.
Because neutrinos oscillate, they absolutely must have mass.
Wow. Okay, so how does that flavor switching actually work?
Well, there are three distinct neutrino mass states. When a neutrino travels, it's actually a quantum superposition of these three states. And because they have slightly different masses, they propagate as waves at slightly different frequencies.
So they interfere with each other?
Exactly. As they interfere, the probability of the neutrino interacting as a specific flavor shifts. By studying that oscillation, scientists can actually measure the difference between the squares of these masses.
And there are two different frequencies of this flavor switching, right? Because one mass square difference is about 30 times larger than the other.
Yep, you get a long, slow wave and then a much faster, shorter ripple superimposed right on top of it.
Okay, but knowing they have mass is one thing. So how did scientists actually figure this out when these things pass right through solid matter?
Well, this is where the story gets interesting.
I couldn't wait to get to this part. I read the massive new study published in the journal Nature on June 10th, 2026 by the JUNO collaboration.
Oh, it's a brilliant paper, and accompanied by a great commentary by physicists Patricia Valle from William and Mary and Zoya Villari from Ohio State University.
The sheer scale of the machine they describe borders on science fiction. I mean, picture this. The Jiangmen Underground Neutrino Observatory, or JUNO, it is located in Guangdong, China.
Yeah, buried beneath Dashi Hill. And to capture these incredibly elusive interactions, they constructed this massive, perfectly spherical acrylic vessel. It's 35.4 meters in diameter.
Which is basically the height of a 10-story building. Just a massive acrylic sphere.
Supported by a huge stainless steel truss.
Okay.
And they filled that sphere with 20,000 tons of a liquid called a scintillator.
And this isn't just water, right? It's
Yeah.
a highly specialized glowing fluid.
Yeah, it's an alkylbenzene-based fluid. It's designed to emit an incredibly faint flash of light whenever a charged particle moves through it. And the liquid has to be perfectly transparent.
So that even a single photon of light can travel across the entire sphere without being absorbed.
Exactly. But creating the light is only half the battle. To actually see that tiny flash, they surrounded the sphere with tens of thousands of photomultiplier tubes, or PMTs.
These act like giant electronic eyes.
Yes,
Yeah.
tens of thousands of them staring inward at the liquid, waiting in absolute pitch-black darkness. And to shield all of this from cosmic rays, the entire detector is submerged in a huge water pool and buried 700 meters underground.
Okay, so they have this incredibly quiet underground environment, but I was looking at the setup, and the geographic location is just mathematically perfect.
It really is. The
Yeah.
detector is situated exactly 52.5 kilometers away from multiple nuclear reactor cores.
The Taishan and Yangjiang power plants.
Right. And that specific distance of 52.5 kilometers is the optimal baseline to catch the slow wave of the neutrinos flavor switching. It's where the electron antineutrinos from the reactors hit the bottom of their cycle.
So JUNO is specifically hunting for these electron antineutrinos through a process called inverse beta decay.
Yes, which leaves a highly distinct signature. It creates a double flash of light.
Like a 1-2 punch. First, you get a pumped positron signal.
Right, the positron flashes immediately. And then roughly 200 microseconds later, you get a delayed neutron capture.
Which gives off a second flash. So the software is just scanning for that exact sequence. Flash, pause for a fraction of a millisecond, flash.
Exactly. That is the gold standard for confirming a true neutrino event.
Well, wait, out of 20,000 tons of liquid, constantly bombarded by radiation from the Earth and space, in their first 59.1 days of data, how many of these reactor neutrinos did they actually catch?
Just 2,379 candidate events.
Wait, really? Just over 2,000 true signals in 2 months from a 10-story detector.
It's wild, I know. It just shows how weakly these particles interact with matter. And filtering out all the noise to find those 2,379 events is a massive undertaking.
I mean, they have to account for geoneutrinos coming from the Earth's crust, right?
Yeah, and accidental background radiation.
Mm-hmm.
But the hardest part is the cosmogenic isotopes.
Like lithium-9 and helium-8.
Exactly. Even under 700 meters of rock, some really high-energy cosmic muons punch through. And if a muon hits the carbon in the scintillator liquid, it creates those isotopes.
And when those isotopes decay, they mimic that exact double flash signature.
They do. So they built a whole active muon veto system in the surrounding water pool. When it detects a muon, the software basically blinds the detector along that specific path for a fraction of a second, just to ignore the fake signals.
It's like the ultimate noise-canceling headphones, but for particle physics.
That's a great way to put it.
Well, here's where it gets really interesting, because the results of this filtering are just incredible. JUNO successfully measured the smaller solar oscillation parameters with unprecedented precision.
They really did. They established the mixing angle, sine squared theta 12 at 0.3092,
Right.
and a mass squared difference of 7.5 times 10 to the negative 5 electron volts squared.
Which is a huge leap forward.
Oh, absolutely. This single 60-day run improved the global precision of these measurements by a factor of 1.6. It is a stunning validation of the detector's energy resolution.
But measuring the solar parameters is just the beginning, right? I mean, if we connect this to the bigger picture, JUNO's real goal is the fast ripples.
Yes. The data already showed an enticing hint of those small ripples superimposed on the main oscillation wave. And decoding those ripples is the holy grail.
Because that tells us the neutrino mass ordering. For the listener, I want you to imagine a ladder with 3 rungs. We know the distance between the rungs, but we don't know which way the ladder is facing. If the 2 closely spaced rungs are at the bottom and the heavy one is at the top, that's the normal ordering.
Right. And if the heavy ones are at the bottom and the light one is at the top, that's the inverted ordering.
So why is knowing this order so profound? Like, why does it matter to us?
Well, it matters for almost everything in astrophysics. Knowing the mass ordering is critical for constraining our models of how the universe was formed.
Because neutrinos are so abundant, their gravity affected how the first galaxies clumped together.
Precisely. It also changes how we interpret signals from exploding supernovae. If we know the mass ordering, we can decode the neutrino bursts from dying stars to understand how heavy elements are forged.
The elements that literally make up our bodies.
Yeah. But maybe the biggest thing is that it sets the stage for understanding why the universe is made of matter rather than antimatter.
Oh, wow, the CP violation stuff.
Yes. If we can pin down the mass ordering, it gives future experiments the foundation they need to prove if neutrinos violate fundamental symmetry rules. It could explain why all the matter in the universe didn't just annihilate with antimatter right after the Big Bang.
That is just mind-blowing, and it brings our journey completely full circle.
How so?
Well, we started by talking about that child safety paper, right? How society must urgently design digital platforms with safety by design to detect unseen harms in the noise of the internet.
Oh, right.
And here with JUNO, we have a triumph of precision by design engineering, an impossibly quiet underground environment to hear the absolute faintest whispers of the universe.
That is a beautiful connection.
So to quickly recap our deep dive today. First, neutrinos, the universe's ghost particles, absolutely have mass because they change flavors over time.
Yes.
Second, the JUNO detector used 20,000 tons of liquid beneath a mountain to precisely measure these changes, filtering out immense background noise to find just over 2,000 true signals.
And achieving world-leading precision in the process.
It's just a profound reflection on human ingenuity. I mean, we started by thinking these particles had no mass and were completely impossible to study. And now we are literally weighing ghosts by watching them change flavors deep underground.
We really are. And I want to leave everyone with a final thought to mull over.
Please do.
Current projections suggest JUNO will need about 6 years of data to definitively distinguish the mass orderings.
Okay.
If this staggering level of precision is what they achieved in just 59 days, what might scientists uncover next when they finally solve the puzzle of the universe's ultimate ghost particle?
Could it prove they are their own antiparticle?
Majorana fermions,
Yeah.
exactly. It could literally prove the mechanism for why we exist.
What an incredible mystery to watch unfold. Thank you all for joining Deep Dive Lab today. If you enjoyed uncovering the scientific mystery with us, please follow and subscribe for more stories just like this one. Until next time, keep wondering about the invisible forces around you. We'll see you on the next Deep Dive.